So we're going to cover chapter 14 in this lecture, and it's talking about glaciers and glaciation. Glaciers are big moving bodies of ice on land, and they cover about 10% of the Earth's land surface. They were really prevalent during the Pleistocene epoch, which is the Ice Age. That's last 2.6 million years. And glaciers have been much more widespread, even more so than the last glaciation. But the last glaciation saw quite a lot of the land area frozen, covered with ice. And these frozen glaciers that we have today do constitute a very large reservoir for fresh water. Basically, the idea is if you get a net accumulation of snow that doesn't melt in the summer, it'll convert from the granular ice known as firn after the snow gets it sublimates a little bit and no longer really looks like a snowflake, and it'll be compacted, sort of like you make a snowball and it become glacial ice. We'll look at the idea of a glacial budget and how that is important for understanding how glaciers change over time. We'll look at how glaciers move through concepts of basal slip and plastic flow. There are certain other factors that determine how fast they move, and we'll talk about those too. And we will also talk about how glaciers effectively erode, transport, and deposit sediment. So here we have a picture of a glacier. It's a painting, I don't know, it's from the 1800s or even earlier. But we know there was a little ice age during the periods from 1500 to late 1800s, and we had the advance. I mean, this is over, obviously, there's 2.6 million years. To 10,000 years ago, there was a huge number of glaciations, or 40, we think 40 to 46, in fact. I don't know if that's a huge number, but it's quite a few. And then we have this cooling trend about 7 to 10,000 years ago. 7,000 years ago it was called the Younger Dryas, where we got the glaciers advancing quite rapidly. Then they disappeared to what we have probably in the 1500s, and then we had a cooling period where we had quite a lot of snow and glaciers advanced up until the 1800s, and then we, of course, humans started producing a lot of CO2, which changed the way the landscape responded and produced ice because it's warming up. Glaciers look different depending on what terrain they cover. Glaciers comprise about 2%, I think the book says 2.15% of fresh water, but here we have a glacier that is obviously a valley glacier because there's a mountain in the background. And what you'll notice when you have valley glaciers is there'll be a U-shaped carved area where they have eroded the underlying rock, creating that specific feature. They're basically, we have these valley glaciers, which are these long tongues of ice that come out from the mountains. They are much smaller than the continental glaciers, and they move from high to low elevation. They'll have tributaries just like streams do. And these glaciers are often called alpine glaciers because they are found in areas where there are no trees, which is the definition of alpine. So all this area up here, there are no trees. There are a few trees right here, but and they look very small here, and they could be small if this is up in Alaska or in that area. These are black spruce, and they are very small. But these ice flows tend to be above the acceptable growing conditions for trees, which is why we call it alpine. Subalpine would be areas where you have trees growing that are below the tree line. We have the valley glaciers that we just talked about, which is the mountain glaciers, the things we normally think of when we think of glaciers, and then we have these continental glaciers or ice sheets. This is Antarctica or Antarctic ice sheet, And what's interesting about the Antarctic ice sheet is it goes up to 4,000, I think this is feet. It could be meters. But I think it actually is meters because it's pretty thick. Oh no, it's got to be feet. But anyway, we have all this terrain underlying the glacial ice in these continental glaciers. We have mountains and valleys and everything else that are underneath the ice, but it's built up so that it's very, very thick. And they flow out to the sea, and they basically produce their own flow because they are as tall as mountains, which means they have a slope. And think of the ridge push slab pull that we talked about when we were talking about plate tectonics. This is the same idea. We have a process by which you build ice up as it accumulates because things, that you get all this snow up in this area, which creates a topography. If you were looking at this from the side, it would look like this, right? It would go up and then come down like that, which means it creates its own slope, and the glaciers move downhill for where the snow accumulates at the top. And so they will actually create their own flow in a sense. The book also references a term called ice caps, which are similar to continental glaciers, but they're very, very much smaller. They don't cover as much area, and they will often be associated with valleys and mountains and flat areas, like Iceland is a ice cap, but it's not very big. If we look at the classic glacier, as we have a picture of one here, they are really slow moving bodies of water. They're frozen, and they are considered minerals, large bodies of moving minerals. And in this case, we have a large main glacier with a tributary, and whenever we talk about a tributary in this sense, it's sort of like a tributary of a stream which meets with the larger stream and coming off from a side channel or a side valley, and it creates characteristics similar to a stream. We'll have the similar kind of erosional features, although they aren't as small. These are much larger, and they go through some pretty interesting processes. We have the glaciers move, but they also will sublimate, which means as they move, you get snow up here at the top. Let me get a pen. You get snow at the top, which adds more snow up here, right? It's falling up here, which adds layers, which creates a flow or a weight and moves it downhill. But as it gets down further and further, since it's so dry in a lot of these areas, think of Antarctica, it's very, very dry, this ice will sublimate, which basically means that it goes from a solid to a gas without passing through a liquid state. And this is where the ice goes directly to water vapor. And we recognize this as one of the primary ways that glaciers disappear. They evaporate, basically. But they don't evaporate from a water state. They evaporate from a solid state. But obviously when glaciers sublimate, it takes a very long time, which means these glaciers are reservoirs for the hydrologic cycle, or the fresh water, and it can be stored for very long periods before it moves back into the ocean, which means the level of the oceans is determined by the amount of glacial ice that we have on the land. So how do glaciers form and how do they move? That's basically where we're headed with this lecture. And here I'm showing you a picture of how snowflakes become glacial ice. First thing that happens is you have these snowflakes. Obviously they look like snowflakes. There's some sublimation that goes on when they land. They're coming down and they look like sort of like snowflakes that have been eroded a little bit, or they're not looking very, very pretty in a sense. This will granulate, which means all of these angular pieces that you see will either sublimate or recrystallize into this sort of granular looking snow. Now be aware that it's already fallen at this point. It's not coming from the sky and doing this. This has already fallen. It's sitting here, sitting on the surface of the snow. It's sublimating. It's melting a little bit. It does refreezes, things like that. And then you get all of these pieces coming together and you produce these huge I guess not huge is the wrong term, but larger pieces of ice that are granular snow that's sort of stuck together. Think of it like a snowball. Now, if you take a lot of this fern and you stick it together and you end up putting it under pressure, etc., as more of this ice and fern builds up on the top, you end up with glacial ice. And one thing that you must be aware of is glaciers are basically winter snowfall that exceeds summer melt and accumulates throughout the years. And remember that it's, if you look at snowflakes, they're basically air. And once you get to the point where you've forced all the air out, just like you make rocks and you crystallize all this material, because it's a crystalline solid, it's a mineral, we end up with a glacial ice. In a sense, glaciers can be thought of as very large, flexible rocks that are moving downhill. So how do glaciers move downhill? Well, when the fern gets buried and refreezes and becomes much more solid, it tends to flex like rocks when they're under a lot of weight, and they undergo plastic flow. So we have a lot of weight bearing down on the land surface. This is all the ice from here to here. We have an area where the pressure from the ice above means that the ice won't fracture, and so it'll actually plastically change. It'll flow. If you look here, we have this one singular sort of measure of the surface showing you how it flexes. So you have basal slip because there's a little bit of water down here that lubricates this a little bit. And as it flows downhill, the surface, the top, because of fracturings and total surface movement, actually cause the internal structure of this glacier to flex, or we can get plastic flow, just like we talked about with rocks. So there's an elastic flow, but this is plastic flow, which means it's not going to return to what it looked like before. And that's how they move. They move through a process of basal slip, which causes a flexing, which is then this plastic bending, this plastic flow, which then causes more basal slip. And so glaciers will surge based upon this sort of skipping type of movement that they do. It's basal slip at certain times of the day where it's warmer, or etc. You can maybe get more snow or whatever, and it causes this whole sheet of ice to move to lower elevation or downhill. When glaciers are moving, they change in response to the stresses occurring on their surface or inside. So plastic flow is a result of stress, right? And then we have these tensional, compressional issues at the surface, which is undergoing some extreme changes due to the amount of weight of the glacier. So we have this brittle zone. So remember, these things under a certain pressure, they will flex or they will be plastic. So under this line right here, this area right here, this is all plastic, which means it'll bend, right? Just like that, and it will flex, or it'll move plastically. Then at the surface, where it's brittle because there's not enough weight to cause those crystals to realign and change, you get openings, right? These are the crevices that we talk. I don't know if you talk about, but if you ever watch these climbing shows, they're worried about them because no one wants to fall inside. Because one thing that we know about crevices is they close back up when they go into the area where you have a compression. Now remember, when we think about tension, that's the pulling apart. That's how the basin and range formed through the accretion of North America as it pulls out into the Pacific Ocean. It's causing a tensional release in the center of the Great Basin there, and you get that basin and range, that fault blocking occurs. And then, of course, we got the compression, which is sort of like when you put the Indian continent and the Eurasian continent come together. Those are compressional forces, and they'd be like the Himalayas. In this case, yeah, you do get some buildup of that ice, and you'll get some interesting features, but it's not like the Himalayas. They're not that big. But bring these crevices back together. So if you fall in one of these crevices, you get squished. That's why we worry about it. So the upper part of the glacier is brittle due to the nature of ice crystals under very low stress or different kind of tension. And then we have these brittle zone going down into about 40 meters into the glacier, where it becomes dense enough because of the pressure from above to flow plastically. Here I show you pictures, of course, from the book, but these are crevices that are opening up on, this is the Kenai Fjords. Oh, I used to live up in this area. I've seen these glaciers in the National Park Preserve near Seward, Alaska. They do also do a race called Mount Marathon up there. It's pretty crazy. You should check it out sometime. I watched it one year, and they have life flight people taking people off the mountain because it's such a crazy run. There are people that have actually started the race, and they disappeared, and we never found them. We don't know what happened to them. It's pretty strange. Alaskans are a little odd. But anyway, I used to live there, and I've looked at these. And basically what you see here is you see the glacier that is flowing, in this case, down the hill. And there's a little bit of tensional opening wherever it's going over these rocks right here, right? And you get these crevices opening up. Then when it comes down to this area where there's sort of a bowl at the bottom, these crevices close back up, and that's what you see right here. Now this takes some time. It's not like you can fall into a crevice and you get killed within like minutes, but even so, most people fall in crevices just die because they fall a certain height. 40 meters is a long way to fall. But anyway, there's something to be aware of, and if you ever go ice climbing, and also be aware of how they form, so you can be sure to avoid them. The crevices give us an indication of what's going on with the glacial budget, and also what the underlying terrain looks like. So you have the glacial budget basically determines how fast a glacier either grows or retreats. We call that prograde or retrograde. But in this case, you have a zone of accumulation, so this would be all the snow, right? Snowing up here, builds up. You have an area where you get firn developing from the snow as it refreezes and melts and refreezes, etc. Some of it sublimates, and you get snow at the top. You get a little bit firn underneath, and then glacial ice underneath that as the firn gets compressed even further, and there's no more air space, and you have one solid block of ice. It's not like individual pieces anymore. And there's a point at which you get an area where there's no longer firn being developed because it's either too warm or there's not enough snow, different terrain, etc. But as you get down to past that firn limit, you get sublimation and evaporation loss, which means the glaciers are getting smaller. They're returning, this evaporating, returning that water back to the air, and it's called the zone of wastage from the firn limit, to the foot or the toe of that glacier. And at the toe, this is where all at the bottom of the glacier you get all the calving. These are the sort of the icebergs, etc., that we always hear about. Not the big ice shelves that break off. This is actually icebergs that are falling into streams, waters, lakes, oceans, whatever. But there's a zone of accumulation, which is very at the top. It's where you're building the glacier, and then the zone of wastage is where you're reducing the amount of ice that's in that glacier. And the distribution for glaciers is where you get sufficient snowfall that doesn't melt in the summer, which means summer temperatures have to be low enough to keep it from melting. And it's sort of like in Michigan, if we were cool enough, if the Lake Michigan froze and was cool enough, eventually we would just build up enough snow in some areas like up by Marquette, and it would never melt, and then it would get more snow, and eventually it would build up over time, and we'd end up getting a small glacier developing up there. I wouldn't count on it anytime soon, but we do know that the lakes are cooler than they have been in the last 40 years. So some interesting stuff is going on. And as I tell people when they talk about, this is the kind of stuff I studied for my dissertation, global climate change is what we're interested in. We're not so interested in the term global warming. It is a process of the accumulation of CO2, but we also know that the Arctic Oscillation that produces these extreme winters is now, because it has more energy to wobble greater, if that makes sense, we'll actually get colder zones further south as that Arctic air moves south due to the greater energy in the atmosphere. So back to how glaciers form. We know that they form in the high mountains, in the higher latitudes, which would be, Antarctica, the Arctic, Alaska, those kind of areas. We also know that these start out usually as snowfields, and there's a zone of accumulation, so snowfield can turn into a glacier. Snowfields are basically just snow and firn, but it's not thick enough or deep enough to actually be a glacier. It's not one solid piece of ice. We know that the lower part, so the upper part is the glacier where the snow is covered, it's year-round. We get the zone of accumulation, and then there's the lower part where you get losses and melting due to sublimation and calving of icebergs, and the zone of wastage. There's basically a persistent negative budget that we have going now with all of the glaciers today, which means that they're disappearing. And we know that Glacier National Park will eventually be without glaciers. And I'm going to show you I'm going to jump out of this lecture for a little bit and show you a very interesting animation that was done by the people that oversee Glacier National Park. Sorry, my screen image here isn't quite large enough to capture this entire animation. So, whoops, I don't want it went black. Anyway, there we go. So it'll go through a whole process here from 1850, 1860, and it'll show you what they've modeled. So all the white that you see on screen are the glaciers and how they've retreated since the 1880 all the way from. This is actually one of the things I talk about in the lab. So there was a little bit of a progression in 1980s, and then they get reduced even more and more. 2030, there are no glaciers left on Glacier National Park, which is pretty interesting. And so there is evidence of global climate change and direct evidence from, well, Glacier National Park. It's not, you guys can look this up. You just look up, Glacier National Park animation. You can download. This is a PowerPoint slide that they've put the animation on, and they've just shown you all of the changes, and then they model the changes that they expect to happen after 2014. And it's pretty interesting. Now back to our slide show. So we have, we're talking about the glacial budget. Now we have to figure out, well, how fast do these glaciers move? And obviously the rate of glacial movement depends on the slope, the discharge, and the season. So in the summer, depending on, if they get a lot of snow, they may move faster, may move downhill faster, but they often retrograde in the summer because they're going to melt quicker. And so some of the fastest movement for glaciers is usually in the transition seasons like spring or fall, because they get a lot of snow. There's a lot of changes in the weather or the atmosphere that create conditions that are very good for lubricating the underneath the glacier, and how much snow they get at the top, and then how fast it's going to move. And they can move several feet a day if conditions are really good. And of course, in general, valley glaciers move more rapidly than the continental glaciers because they're moving at a greater, they're on a steeper slope. But continental glaciers, they move at about I don't know what, a velocity of several centimeters. And they can move at several meters a day depending on how big they are, obviously. And then some glaciers, like the valley glaciers, they can move several meters a day, which means they are moving rather quickly. It also depends on what kind of underlying surface is it type of rock that they're moving over. One of the misunderstandings about glaciers is how do they erode and create these physical scars that you see on the surface of the Earth. One thing that we know is glaciers don't actually, the ice itself, because it's very soft, doesn't do the actual abrading, in a sense, when we talk about abrasion. It does bulldoze because the weight of the ice will push down and cause a depression, and it'll doze up or bulldoze up. So if you think of a big piece of ice, right? Big piece of ice that comes down, it's going to put pressure on the ground around it, and it'll push ahead of it a bunch of debris, which is, we'll get glacial moraine. We'll talk about that. But in most cases, they'll bulldoze loose material in the front of them, and they erode by abrasion, which means that they pick up other rocks and debris, and those rocks and debris then abrade or scratch the surface of what they're moving over. So in this case, we see that there's abrasion right here. As this ice moves over the top of this ridge, you end up with these boulders that are in the ridge, right? Or, no, sorry, in the ice, end up gouging out the ridge as they move over. And then on the other side, you get this plucking as this comes over and there's more water available, as there's a little bit of a pressure release, sort of the boot effect that I've talked about. It'll pluck out these boulders, which then will get caught up in the ice, get refrozen, and they'll end up they're going to pull the material off this side as a bunch of debris, and also keep moving in that direction, and then do more abrasion as it moves down stream as far as the ice flow is concerned. And this is what it looks like. So this is probably a picture. This is it looks like a Causeway of the Gods or something like that. If you look in Ireland, I think that's where this would be seen. That you basically had this big ice sheet that went over the top of this, and obviously it was moving in this direction and abraded the surface of these basalt columns. And here, what they're showing you is not this rock formation, but this is glacial milk. So all this looks like it's like a white, milky colored water. This is actually not as milky as some other glacial milk that I've seen. I've seen some that is very, very white, to the point where it does look like milk. It's hard to tell the difference. The valley glaciers, as they erode, they turn the V-shaped valley into a U-shaped valley. And I have a whole bunch of pictures of these kind of U-shaped valleys from Colorado because it was glaciated quite broadly during the last glaciation. You have all these high elevation U-shaped valleys. And then there's the fjords where you have the U-shaped valley. As that glacier went into the water of the ocean levels were lower, which means you get the ice abrading lower in sea level because sea level was lower. And then when the ice receded, since it melted and went into the ocean, that water then, the ocean water rose and it filled in those valleys, and so we have these things called fjords. And these are the structures that you get when you have glaciers coming together. These are a lot of French names, and so I'm going to mispronounce them. I'm sorry if you take French. But we have this hanging valley, which basically is the glacier. He has tributaries that come down into this area. There's a big glacier right here that's going down through this direction right here. And there are all these tributaries coming down here into this area, and they're causing their own U-shaped valleys as they do that. But you end up producing a hanging valley, which is an area where once the ice melts, you end up with a valley that is sort of seems to be perched on the side of a cliff. And then you have the horn. Think of the Matterhorn that you find in the Alps, and this is where you have glaciers on either side of this, right here and right here, and they erode away the surface, make the U-shaped valley, but then they leave the point at which where a lot of the snow is falling that's not deep enough to erode that area. And then you have an arete. It's again, I'm sorry, Laura, she speaks French, but an area where you have it's hard to see this ridge right here that's coming down from the horn. And then you have a cirque. These can be filled with water and be lakes, which we call tarns. I don't know if that's in the book, but that's what they're called. They're called tarns if it's a cirque that's filled with water. And then we have these truncated spurs, which obviously they're glaciers on either side moving down this direction, and this is sort of a spur. It would be a point on the side of a mountain. In this case, it's a cliff or a very steep slope, and then another ridge that comes to the end at the top of that steep slope, and that would be a truncated spur. And then, of course, we got the U-shaped valleys at the bottom. There's also U-shaped valleys here, which create these hanging valleys and everything else, but be aware of it. They look that way due to the activity of the glacier. And then, of course, we got the remnants or the land surface that is developed from continental glaciers and the erosion from those continental glaciers, and we get these lakes and streams that are connected in a very haphazard manner, and we call this, well, you've already heard it, it's called a deranged drainage system, and that's because all of the kettle lakes, where you get big chunks of ice falling off the glaciers, they fill up. You have these other lakes that are moving in with streams connecting them, and the water table and the structure of the land takes the shape of what the ice looked like and how it eroded the land surface rather than the water movement, because there's not a lot of ridges and the water doesn't move very rapidly. So it's the results of the ice rather than liquid water. Glaciers also move large boulders called erratics in their glacial drift. Glacial drift is just the general term for glacial deposits like moraine. We'll talk about some in a second, but in this case we have these boulders that have moved several thousand miles from their original substrate. So if you look at If you go to the Dahlem Center, if you ever get the chance to go out there, they have a very large pudding stone sitting out front. And that thing, I think, was moved 1,500 miles or something from up in Canada. And that's the result of glaciation and pushing that down. Obviously, it wasn't at the Dahlem Center at one point. A geologist found it and they moved it there, but it was found in Jackson County. And here we have the till, or the end moraines. The moraine is just sort of like these glacial drift. End moraine is one of the glacial drifts. In this case, you'll see this glacier here, and it's hard to see in this picture, but there's the end of the glacier is right there. There's some drift right here. I don't know what, I think that's drift right there. There's some drift right here. There's drift right here. There's drift right here. Where it's been deposited as this thing retreated, you have different zones where the drift was deposited over time. And so we definitely see how rapidly glaciers can disappear. I mean, they can disappear in 100 years or even less. And there's a very interesting video that I put online for you guys where the Smithsonian goes and looks at how they date glaciers and how they look at how fast they're moving in their relation to CO2 and global climate change. It's pretty fascinating. And in this is what they're showing you is the end point for the moraine. This is the end moraine, which is a crescent-shaped deposit of till that formed near the terminus, which is the end of the glacier. It's a big pile of rubble right at the front of the glacier. One thing to keep in mind, and I have this in the notes, is there's a difference between glacial till and stratified drift. So glacial drift is just the general term, but glacial till, which is a type of drift, is sediment deposited directly by the glacial ice, which is that all the plucked rocks and everything basically get dumped out at the very end. They're very poorly sorted, which means they're big ones, small ones, sand, all sorts of different stuff, kind of where we are in Michigan. And then you have the stratified drift, which is sediment that's deposited by running water, which then, like these braided streams, well-sorted ground moraines, which look like, they have large boulders at some areas, just like when water makes, it produces that in streams. And that's due to till left by a retreating glacier. We have different types of moraine as well. There's ground moraine, which has sort of a rolling topography like we have at the end of where we are in Michigan. If you go down to south of Jackson College, you'll see two big piles of rock. I don't know if you'll notice in that, and those are called kames, which is another type of moraine or glacial drift that's left behind. And it's a rolling topography, whereas a lot of these elongated ridges at the end of these large glaciers, these are the terminal moraines. In your book, and that's why I show you these, they have a good example. They show you both the what it looks like while it's glaciated, then what's left over. So you have the terminal moraine, which is the point where it goes the furthest. You have the emerging subglacial stream, which is, if you were to go into that glacier, you would end up seeing an esker, which we'll look at in a second. And this is a retreating ice front. And then we have these kames, which are just deposits from accumulations of rock and material in the ice, and usually they get melted first because they create a hot spot or a warm spot, right? That positive feedback effect, which is also a video that I ask you guys to watch. And then you have the outwash plain, which is where we are in southern Michigan, basically. It's all this sort of swampy, deranged drainage system that we have. And then, of course, the terminal moraine again. So there's terminal moraine over here. It's cut by the stream, terminal moraine here. And then you have these ice blocks that get buried, covered by moraine, etc., and then they melt. And so if you go over here, we get the kettle ponds. We have these drumlins, which shows you the direction of the movement of that glacier. So it'll dump a bunch of material and then keep moving over that and produce these long striated sort of hills. And then you have the kames, which we have south of the college, which are just big deposits left over. They're sort of like dumped all at once. And then, of course, the esker, which is the stream. It's like an inverted stream. So you have a stream bed here. Let me erase this. It's getting pretty messy. You get the inverted stream inside a glacier due to the movement of that of the emerging subglacial stream melting its way through that glacier and depositing material. So here's the esker, right? It starts here and then moves down through right here, and then there's where it opens up, deposits a lot of material, and becomes a stream. So the stream has this U shape to it because it's just eroding the ground. And then if you go back to where the esker is, it's the opposite. It's like a hill. And there's an esker down. If you go down to the McCready Reserve, there's an esker I don't know if it's the Blue Ridge esker, but it's one of the eskers that goes through Michigan, and you can actually go down to the McCready Reserve and go see it. It's on the south. It starts at the south east side, I think, and then moves north. And it's just it's the hill that moves. You know, if you go on those trails, you'll see a hill at the very external part of the property, and that's actually an esker. And here's what those deposits look like when you're looking at a glacier that's still around. So you have these lateral moraines. Obviously, lateral moraines would be the sides. Medial moraines would be in the middle. That's where two glaciers come together. So you have your medial meniscus, which is on the inside of your knee, and you have your lateral meniscus, which is on the outside of your knee. And so that's kind of how you look at it. Lateral, outside, medial is inside, and these are ridge-shaped deposits of till that form within the glacier, and that's created by all these plucking rocks that get ground together, and you produce this gravel and a bunch of other stuff, and it gets deposited over time as the glacier moves downhill. And I'm just drawing your attention to this picture in the book. This is the recessional moraine, cames, eskers, drumlins. The ice is gone. I like that, ice gone. Anyway, and the kettle pond's an abandoned outflow channel. So obviously it's no longer a stream, so they call it abandoned. I'm going to go through these rather quickly because you can look at these in the books. But we have the cames, which are the conical hills created when stream deposits sediment in a depression on the glacier's surface, will melt through and gets deposited all at once. These are, glacial meltwater, and it's usually well sorted, which means you have big boulders on the surface. And if you go out there, actually, south of the campus, you can see where the bigger materials at the surface. There's a few areas where it's been dropped later, and you actually just have the same size boulders represented, and then there's some at the bottom. And that's because of the movement of the water and how the smaller stuff tends to filter to the bottom. The larger stuff stays at the top. It just takes up more space. And here's an esker. It's like that snake-like deposit where you have, it looks like a snake. It's an esker, but it looks like an esker. I like that. But anyway, so here we have something that goes down this direction. This is the direction of the stream. It was coming down. This looks like it's the deposit where the stream came out. The outflow was over here rather than on this side, but I could be wrong. These are pretty cool. I mean, go check one out if you can go to the McCready Reserve. It's a pretty cool little formation. And then we have these deposits called varves, which are really cool because you can determine how many cycles the glacial lake went through before it got filled up, or it could still be there. We can actually core these things and figure out what was going on in the past, depending on how thick the varve is, which is, the dark and light layers. So the dark layers are usually the organic material that's deposited in the winter when the algae that grows in the summer dies off, right? Because the light layers, this is basically you get runoff in the summer, which is that glacial milk, and it's in a lake, and as it settles out at the surface of the lake, you start to get these algae blooms, just like we have in Michigan. And then in the winter, when you cap that off with ice, that algae dies and produces a dark layer underneath as it settles out into that mud, that white layer that was already there. And we can actually determine the age and the history of any glacial lake using the varves. It's pretty cool. It's actually, I love it. It's really interesting. So, what causes ice ages? Well, we know that the ice ages that appear every 22 to 24,000 years are the result of the Earth's precession around the sun, which is as the Earth moves around the sun, it is closer or further away in the summers or the winters, depending on when it is. My students get a little confused when they see this picture. Well, you guys are my students, so hopefully you won't be confused. But right now, so we're in the summer, and that's right here. I mean, if we're in the summer, we're not in the summer. We're actually coming in the winter. July, we're further away from the sun, so the distance from here to here in the summer is longer than the distance from here to here in the winter right now, which means that it's actually not as cold in the winter than it could be if we were at the opposite sides during full glacial cycle, barring the CO2 concentration of the air, obviously. And in this case, July in the north, right? July would be winter, which is normally our summer, right? If you think about it, and we have January, we're further away in January, which is now our summer because of the tilt of the Earth, which means that the amount of radiation coming in during summer doesn't heat the Earth as much, which means it stays cooler, just like what we have going on with the Great Lakes right now. We know that Lake Michigan, because we had such a cold winter last year, it's like 6 degrees cooler than it was. I don't know. It's just much colder, and it's icing over sooner than it has in the last 40 years. Which is also something I tell people when we talk about global climate change. We're not talking about global warming. We're talking about global climate change, because we know that the Arctic Oscillation, which gives us the kind of weather that we have in the winter, will oscillate more, just like I was saying before. The greater the oscillations, which means we have worse winters. So if you look, the precession over at the top right here, what it looks like as it spins around the sun and how it moves on this 23-degree axis, and the direction of the Earth towards the sun at these times will change the way we have glacial cycles or not. And the guy that figured this out was called Milankovitch, and it's called the Milankovitch theory now because it's been tested and looked at for many hundreds of thousands, if not millions of times. So it was a hypothesis at one time, and now it's a theory. And so we have the situation where in the summer, during the glacial cycle, the summer that we would have now in July, let's say, is actually our winter. But we're closer in the winter to the sun than we are when we're in the interglacial, which means that there's not a glacial. We don't have glaciers. So basically, we get much colder in the winter, which means the lakes and everything else respond by getting frozen much more. And the snow that builds up, we have much more snow that builds up, and it doesn't go away in the summer. There's some interesting things that go on when we talk about short-term climatic events. We know the Milankovitch cycles are measured on tens of thousands of years, which means about every 25,000 years we're moving one, going back to the other. And they're too long to explain these small little ice age events and everything else. It could be, solar radiation, volcanic eruptions. We really don't know. It could be a combination of several things. We do know that there tends to be a buildup of CO2 right before we go into these really heavy-duty glacial cycles. So we don't really know if the ocean currents are going to change direction at some point because they're going to become too acidic, which then means that the calcium carbonate that's building up, which is an alkaline, it's sort of a buffer, is going to build up to a point where it falls out of solution because there's too much of it due to too much CO2 getting absorbed by the oceans, and we end up with this big calcite layer at the bottom of the ocean, and the ocean currents change because the density of the water changes, just like we talk about the density of the rocks. And as that changes, it changes where the warm water moves, and instead of going all the way up through, let's say, up towards around Iceland, which is where we think it goes now, and let's say it goes to the Horn of Africa, it comes across where it's below Florida is where it would be coming across, and so that heat pump, the ability to move that heat from the ocean up north to England and Europe would be gone, and you get glacial ice developing very rapidly up in Europe if the ocean changes its currents. And that's something we're worried about as a climate scientist, that if this happens rapidly, we're in for some big surprises. So in conclusion, we have the Pleistocene glaciations. They've been going on for the past 2.6 million years. There's been a bunch of glacial cycles that go back, many hundreds of millions of years. We have some that actually go back to the Pliocene as well, which we didn't talk about. But we think there have been about 40 some odd glaciations in the last 2.6 million years. And we know that glaciers are masses of ice which move over land by plastic flow and basal slip. We know that glaciers are reservoirs in the hydrologic cycle where water is stored for long periods of time, and it moves water from the oceans to the land and back to the oceans, but it's very slow movement, which means it sets the ocean levels and what kind of animals and plants grow on land, etc. And then we have the rate of glacial movement depends on the glacial budget, how much snow they're getting, how warm it is, what time of the year, etc. And then we have the scarring that occurs from glaciers as glaciers effectively erode, transport, and deposit huge amounts of sediment because they're moving large solids, boulders as big as houses that rub into other boulders and crush them and create these scars on the surface, and that's where the erosion actually comes from, because remember, the ice is too soft, except for the bulldozing in front, to effectively erode the bedrock. And then we have the Milankovitch theory, which is an explanation of the onset of large glacial episodes. But then we have some that are very interesting that occur like every 100 to 200,000 years. They're huge. I mean, there's like 90% of the Earth gets covered in ice. Or maybe it's not 90%, but it's 70. I think it's 70%. I'll check on that. But it's much larger than the last glaciation, which was 40 to 50% of the Earth. And we don't know what causes that. We have no idea. Anyway, that concludes this lecture. This is the last one before we have to take a test. So remember, we're going to be taking an exam probably next week after Thanksgiving. Thanks.